Hi, now that you saw how the 2D shape change occurs, now let's move on to 3 dimensions. The first idea is that instead of looking at triangles, now we look at tetrahedra, that is 4 triangles together. Just to give you an idea, so what happens is that we start out with a tetrahedron. I hope you can see this tetrahedron. Can you see it's like a corner of a cube, right? And you can see that the y-axis in blue, the x-axis in blue is pointing towards you, the y-axis is pointing sideways, and the z-axis is pointing upwards. Can you see that? So that's the original tetrahedron. And what happens to that is that it gets cubed. What I mean by that is it looks like this. Can you see now the x-axis, the blue line is pointing somewhere else, the red line is also pointing somewhere else, and then the what used to be vertical is now at a steep angle. Can you see that? So what happens is the following. There's the original shape. You can see the three things. That's the x-axis, that's the y-axis, and that's the z-axis. And what happens to that is it becomes cube. In particular, originally we have 3 perpendicular vectors. They may not be unit vectors, they're just vectors, small vectors. Remember, these are all local shape change. Okay. So what happens to them is that they become 3 vectors of possibly different lengths and orientations. So you got to understand that they change their lengths and they change their orientation. Okay, that's how they work. Okay, so now let's see how we can actually quantify this thing. So here is my reference and current shape. So that's this and this, right? So what's going to happen is that I am going to open it up into 3 rectangles. 3 triangles. I'll show you. So if it is like this, can you see x, y, z? What I'm going to do is I'm going to open it up and flatten it out like so. Can you see that? Now you got 3 triangles. So now we are back to the 2-dimensional case, so to speak, because we have 3 triangles, and if you can see the shape change of the 3 triangles, we are done. So what happens is the final shape, which looks like this, is also going to be opened out like that, right? So here is the original shape and here is the final shape. Can you see those 2 things, right? And what we are going to do is we are going to align the blue with the blue and so on. Okay, so what we are going to do is that if you open that, it will look like this. I showed you this kind of shape, and one of the axes will be aligned and one of the planes will be aligned. I'll explain to you in a second so that we can see the shape change. Okay, this is how we are going to look at shape change. Okay, very good. So how do we do this? Here's my original, and I have marked the points A, B, C, D, and then here's the deformed shape, and here's what A, B, C, D looks like. Very good. So what we are going to do is we're going to first say we're going to create a local coordinate system so that we can talk about deformations. So the first thing we do is we draw an x-axis along AB. You can see that x, that's the blue line. The y-axis is perpendicular to AB and in the plane of AB and BC. That's the base plane. That's this base plane, ABC plane. And the z-axis is going to be perpendicular to all 3. Okay. In terms of these things, in terms of this local coordinate system, it's pretty easy to write down what is A, what is B, and what is A, B, C, and D. For example, you will see that B has only an x component. Bx 0, 0 because it's only along the x star axis. C has only an x and y component because it's in the xy plane, and it will be Cx, Cy 0. And D has all 3 components because it's sticking out somewhere, dx, dy, dz. Okay, that's how it works. Now that we have our components and local coordinate system and so on, we can now talk about how much is the deformation. So that's what we're going to go next. So this I'm going to do like a summary so that you can see how it works. Here's the original, here's the deformed shape. Now we are going to define some things. So we're going to define the vector f1 equals limit B, C, D goes to A of AB vector divided by the length of AB, F2 equals same limit as AC vector divided by length of AC, and then F3 equal to limit AD vector divided by length of AD. Now, why the heck do we do this division, and why are we taking limit? The reason for taking limit is because I want to define fields. You remember, I want to define it at a point. So if I do this business, now it is actually at 4 points. So I got to get B, C and D to get towards A so that I can define something at the point A. That's item 1. But when I do that, if I don't have this denominator ratio, what will happen is that these lengths will go to 0. You see what I mean? I'll just get 0 if I don't divide. What we are saying is both the reference shape, the reference tetrahedron and the current tetrahedron are both going to shrink to 0, but in such a way that the ratio does not. This is classic limits like what you did in your calculus class. So that's how it works. Okay. So these three are the vectors, and the F matrix or the F tensor is defined as F1, F2, F3. So this is called the deformation gradient tensor. Okay. In our case, we can actually write this down. So if you look at F1, that's that guy. So F star, the matrix, equals limit little a, little b, little c tending to capital BCD tending to A. So that's the limiting process of Bx divided by magnitude of AB 0, 0. Because the other two things are 0. Then I'll get Cx divided by magnitude of AC, Cy divided by magnitude of AC 0, Dx divided by magnitude of AD, dy divided by magnitude of AD, and dz divided by magnitude of AD. Can you see? I get 6 components. 3 of them are 0. The diagonal components represent axial strains. It tells you Bx over AB, so that tells you length over length. Can you see that? Cy over AC tells you length over length. Dz over AD, that's how it works. So these things are the axial strains. These things are the shear strains. Can you see? Cx, motion in the x direction divided by distance in the y direction. AC is the distance in the y direction. Can you see that? And then motion in the x direction divided by distance in the y direction. So these are all represent shear stretch. These 3 things represent axial stretch. So this will be called the engineering stretch. Oops. And then we can define what we want is Lagrangian strain is the only one I'm going to define for now, because I want to show you how that works. It is 1/2 F star transpose F star minus identity. Remember, it was lambda squared minus 1. Now it is 1/2 F star transpose F star minus identity. And this will turn out to be, this F star transpose F star is called the C matrix, Cauchy-Green stretch. That's what it's called. Who cares what it's called? Okay. So what matters is these 6 numbers. The F star. Okay. That's how it works. So this is very important. So what I would like you to do is stare at it, make sure you understand, and then because we will use this pretty heavily. Okay. So this is the core idea behind measuring strains and stretches and changes of shape in 3D. 2 dimensions basically means we suppress some of these things. So if I suppress this, I'll get the 2-dimensional version. Okay, that's how it goes. 1 dimension is just this one corner. Can you see that? 1 dimension, 2 dimensions, 3 dimensions. Everything is in here. So you need to pay attention to this. This is how we measure stretch or how things deform. Very good. Now what about stress, force intensity? Well, we are only going to talk about, we are not going to talk about true stress. What we are going to talk about? Engineering stress. So here is my original shape. I'm going to deform it. Here is how it is deformed. Now let's look at the plane that's perpendicular to the x direction, which is original x star direction. Original x direction, which is the plane ADC. And on that we have a force. This is force on plane ADC. Right? Similarly, you will have a force on the plane that's BCD, and then a force on this, but this is supposed to be pointing backwards. So please remember, it's on the plane that you cannot see. It's on the backwards plane. Okay. Now we can define the following things. The engineering stress components: P star 11. Take this force, find its component in the x star direction, and divide by the area of ADC. Can you see? ACD. So force over area. So this will be force on face divided by reference area and limit. So you do the same thing. P star 21, P star 31. That's how it goes. You can do the same thing with the other forces. When you do that, you will get 3 lists. So this is force intensity on the face ADC, on the back face. This is force intensity on the plane ABD, that is this face. And this is force intensity on this face. And please remember, there is a gigantic negative sign in front because the faces are all pointing away. Okay, and that's the end of it. So I hope you got the idea. Thank you.